So in last lecture we discussed about the thermistor, and during the discussion we discussed that in thermistor we generally use a material which has the negative temperature coefficient, means the resistance of that material decreases with the rise in temperature. Now, in case of thermistor, the variation in resistance with respect to temperature is non-linear. Now, relation between resistance and temperature in case of thermistor can be given by one expression. It is given by the expression RT1 is equal to RT2 then exponential one by T1 1 by T2 with this expression, right? Here RT1 is resistance of thermistor at T1 temperature. RT2, this resistance of thermistor at T2 temperature. And here in this expression, this exponential term, it shows that the variation in the resistance with respect to temperature is exponential. And here this beta is the material constant. So this constant depends upon the material by which we have manufactured the thermistor. Depending upon that particular material, this constant is having different values, but it is in the range of 3500 to 4500. And here this T1 and T2, T1 and T2, they are the temperatures. Now we have discussed the characteristic of thermistor, and at that time we discussed that this type of curve, here it is on x-axis, this is temperature, and here it is on y-axis, resistivity. So curve is like this, right? It is a non-linear curve. But if you see the non-linear curve, now if you see the non-linear curve for smaller distance, for the in the x-axis for this temperature T1 and T2, for this temperature range, right? In this temperature range, you can find this is this portion. You can find it as a linear, right? As a whole, from this, suppose this is Tx temperature and this is Ty temperature. Between Tx and Ty temperature, the variation in the resistivity is non-linear. But if we take a small range of temperature, then in that small range of temperature, the graph will be linear. So mathematically, linear approximation of this expression is done, and after doing that linear approximation, this expression is derived in this form. RT1, this is equal to RT2 1 plus alpha delta T. Right? So here this RT1 is resistance at T1 temperature. RT2 is resistance at T2 temperature. delta T is T1 minus T2, difference between these temperatures at which we have measured the resistances, and alpha is resistance coefficient of material. Okay. So, and in case of this thermistor, this alpha is negative, because in thermistor we use the material which has negative resistance coefficient, right? So this is the linear approximation of the previous expression. So this expression can be used if this T1 and T2, these two temperatures, T1 and T2, is of smaller range, right? Then that particularly in that smaller range, the non-linear graph can be seen as a linear, right? So this expression generally people use to find out the resistance for the calculation of the various things. Now, I will take one example. Let us assume the resistance, right, at 25 degrees Celsius of a thermistor is 100 ohm. And let us assume this alpha is given. Alpha is 5% in the temperature range 25 degrees Celsius to 50 degrees Celsius. So this is the temperature range. In this temperature range, so in this temperature range, the non-linear curve is linearly approximated by this expression. And in this case, in this temperature range, the value of alpha is 5%. Now we have to find out the resistance at 35 degrees Celsius. What will be the resistance of that thermistor at 35 degrees Celsius? Right? So now if we put the values in this expression, we have to find out this at 35 degrees Celsius. This is equal to RT2 is this we take it as RT2, this is RT1, right? So RT2, this is resistance as 25 degrees Celsius, it is 100 ohm, 1 plus alpha, this is 5%. And since we are talking about the thermistor, so in case of the thermistor, this alpha, which is a temperature coefficient, it is minus, because resistance decreases with the rise of temperature. So this is considered as minus. So this will be, so here I can use it in this way, minus 5% means 0.05, okay, multiplied by delta T. Delta T is the difference between the temperature 25 degrees Celsius and 35 degrees Celsius. So 35 minus 25 is 10. So in this way, if we calculate, this is 10, how is it? This is 100, 1 minus 0.5. So this is 100 into 0.5. So this is 50 ohm. Right? So in a thermistor, if the resistance of the thermistor at 25 degrees Celsius is 100 ohm, So the resistance at 35 degrees Celsius will be 50 ohm. If the thermistor is made up of a material whose temperature coefficient is 5% in the temperature range of 25 degrees Celsius to 50 degrees Celsius. So in this way, so basically, if we are using a thermistor for the calculation of the temperature, then if the resistance of that thermistor has been changed from 100 ohm to 50 ohm, this means the temperature has been raised from 25 degrees Celsius to 35 degrees Celsius. So in this way, we have to design some calibration circuit or some other interfacing circuit which can be used for the detection of this change in the resistance. Right? In this way, we can calculate the temperature. Now the second point is, the second thing which we will discuss, second type of this thermal sensor is RTD, right? Resistance Temperature Detector. This RTD, Resistance Temperature Detector, it is made by using positive temperature coefficient material, right? So to make this RTD, we have to use positive temperature coefficient material, in those materials whose resistance increases with the rise in temperature. So basically we have to use here metals. In last lecture we discussed that if we increase the temperature of metal, then its resistance increases. So metal is basically used here. So, and platinum. Platinum is used to make RTD. Right? So in industries also, RTD is used in the industry for the measurement of the temperature, and the basic material used is platinum. Now, platinum is having some property due to which this material is mostly used in RTD, manufacturing of this RTD. And what are those properties? First thing is properties of platinum, due to which it is suitable for RTD. One point is it shows linear variation in the resistance with reference to temperature. So, linear variation of resistance with respect to temperature. In case of thermistor, we have seen there is a non-linear curve, but here in platinum the curve is linear. Now another point, it is less contaminated, right? So since this RTD is used in the industries for the measurement of the temperature, so we have to use a material which does not get affected by the surroundings. Okay. Now, in last class, we discussed about the characteristic. At that time, we discussed that in case of thermistor, this type of curve we discussed. Here on x-axis, this is temperature. Y-axis, there is resistivity, right? It is 10 to power 2, 10 to power 4, 10 to power 6, 10 to power minus 2, minus 4, minus 6, minus 8. Here it is minus 100 degrees Celsius. 0, 100, 200, 300. Okay. Now, in case of thermistor, this is 10 raised to power 5. Resistivity, it is in ohm meter. And at 300, it is 10 raised to power minus 2. Okay. So this curve was for thermistor. Right? It is somewhat like this. Like this. Now, in case of platinum, at minus 100 degrees Celsius, it is having the resistivity of 10 raised to the power minus 8. At 300, it is having a resistivity of 10 raised to the power minus 7. Right? Here 10 raised to minus 7. Yes. This is of platinum. So, in case of platinum, for this range of the temperature, the variation is of the order of 10, right? So, because here this resistivity is 10 raised to power minus 7 ohm meter, and here at 100 degrees Celsius, this is 10 raised to minus 8 ohm meter. So, from minus 100 degrees Celsius to 300 degrees Celsius, the variation in the resistivity in case of platinum is of the order of 10 raised to power 1. Whereas in case of thermistor, the variation is at minus 100 degrees Celsius, the resistivity of thermistor is 10 raised to power 5 ohms meter. At 300 degrees Celsius, it is 10 raised to the power minus 2 ohm meter. So 10 raised to power 5 and 10 raised to power minus 2. So here in this case, it is 10 raised to power 7. By the factor of 10 raised to power 7, there is a variation in the resistivity. Whereas in case of platinum, the variation is of the order of 10 raised to power 1. So one thing is there, in case of thermistor, the variation is more, right? So variation is more, so sensitivity of this device is more. Whereas in case of platinum, the variation is not that much more, so sensitivity is less, but this variation is linear. Whereas in case of thermistor, variation is non-linear, right? So these are the difference between RTD and thermistor. Now, construction, it is made up in this way. this is one glass plate, and here we are having the element, that is
Click the Add to Chrome button to continue.
platinum, right? Next, this is a glass. To give the strength to this device. So here, this is element, this is glass cover, this is mounting thread. So on these mounting thread, this device is hanged in that atmosphere or in that particular place whose temperature we want to measure, and these are the leads, right? So this is about the construction of this RTD. So now in next lecture we will discuss about the thermocouple, and if time permits then we will discuss about the IC based temperature sensors.